Welcome back. I've discussed with you the example of the sign lattice and why that might be useful. But next, I want to define a bit more formally what a lattice actually is, and in order to be able to do that, we need to understand what is the least upper bound on a partial order, like I showed it to you. So let's assume we have some partial order that you see here. Then the least upper bound is basically defined as follows. So I'll just show it to you graphically, and you can read the formal definition at your own time at home. So let's assume we have a subset of the elements in that partial order, and let's call that A. Okay. Then you can have several upper bounds of the elements in A, right? And you can see that if we assume that all of these elements up here, they are actually larger than the elements here because they are in this ordering defined by these arrows, then all of D2 and D4 and D3 are actually upper bounds for all the elements in A, right? Because they're at least as large as the largest element that you have in A according to this ordering, to this partial order. But there's only one unique least upper bound among those, which is D3 here, right? So D3 is the smallest upper bound of the upper bounds that I just showed you, and therefore we call it the least upper bound. Okay. Now, based on that, we can have the notion of a lattice or also a complete lattice. So again, let's assume we are choosing some subset of elements A in this partial order here. Then if we demand that we have to have the situation that such a least upper bound of these two elements here exists, right? So we have to have a common upper bound of D2 and D4. If this element has to exist, then we are talking about a complete lattice, and this has to exist for all arbitrary subsets A of U, right? So given any choice, any subset of elements here, I always have to be able, so to say, to merge these two elements, right? So you can also say we are merging D2 and D4, and that has to result in another element that is still part of this partial order, okay? We cannot have any situation where this is not the case. And so if you now look at this partial order that you see here, then in this one direction, this is true, right? So if we now merge upwards for any two elements that you choose, you're always going to be able to merge them. We can also even merge D4 and D6 because then D6 itself is going to be the least upper bound of that set. If we do it the other way around, we still have a problem. So if we wanted to find a merge of D1 and D3 in sort of into the bottom direction, we would still be missing that. And for a complete lattice, we are in fact demanding that these bottom elements here, they also exist, right? So in essence, we need to have such a top element and we need to have such a bottom element. And you can even prove that if you have a complete lattice, then there is a unique element such as this one here and a unique element such as this one here. And that's why also you can just give them a name. And we typically call this element here the top element because it's the unique one, and the unique bottom element down here. So this is the least upper bound of all the elements in this partial order. And this is actually the greatest lower bound of all the elements in this partial order. And if we have this setting, then the resulting structure that you see here, that is actually called a complete lattice. There's also this notion of a semi-lattice, and that's essentially if only one of these exists, right? So if I go back to what I had here, sorry, this one here, right? So that's essentially a semi-lattice. We would be having this unique upper bound, right? But not the lower bound. As it turns out, for most program analysis, what you really actually only need is a semi-lattice, because as we will be seeing later on in program analysis, you're typically only computing and merging into one direction. And in this direction, you want to make sure that you have this property that at some point you cannot go any further, but you also always can merge two elements, as we are showing here. In the other direction, it doesn't matter much. So typically, a semi-lattice, if it's chosen in the right direction, is sufficient for program analysis. If you look at these partial orders here, these are just some more examples of partial orders that are lattices, right? Because they all have this property that I showed you. For each two elements here, for instance, they have a unique, least upper bound, so you can just merge to it. And they are also even complete in the sense, right, that there is a unique top and bottom element. These here, they are not lattices, right? Because, for instance, for these two elements here, you have the problem that you cannot actually merge them, right? So there is no least upper bound for these two elements. Here you have the problem that, well, you can merge them, but it's not clearly defined what the merge would be, right? So if you merge these two elements, you could end up here or there, so you don't have a unique upper bound of these two elements here, and that's also not allowed. So these are not lattices. I still want to say a couple of words about these top and bottom elements because some of you might actually be already familiar with the scientific literature, or some of you might also want to read some scientific papers on the topic. And then you need to be a bit more careful because in scientific papers you will find several different schools, some of which flip the meaning of these top and bottom operators and also the related lattice operators. That's a bit unfortunate. This has historic reasons. So there are some people who are more oriented towards the US and others who are more oriented towards Europe and in particular France. They tend to have sometimes the opposite meaning of what's published in some of the US papers. None is better than the other. Both is fine. It just means that when you're reading one of these papers, you really have to make sure that you're understanding the concrete meaning of these operators so that you're not getting confused by the particular notation. In this course, we will stick to the definitions that were just presented. So in this course, we always have this idea that your program analysis typically starts actually at the bottom. So bottom is typically actually your initial domain value that you use to initialize certain values about which you don't know much because they haven't been initialized, for instance. But then the analysis will move upward in your lattice, and the top value in this lattice is then the most coarse-grained approximative value that you can think of. It basically means I don't know anything anymore about this particular value in your program. It could be anything, right? So that's the semantics of the top value. I want to show you one more interesting lattice because that shows you one more problem that we haven't covered yet, or one more challenge, let's say. Let's look at the so-called interval lattice. So an interval lattice is a lattice that's also very popular in constant propagation, and it's somewhat in between the lattice that I showed you initially, where we were assigning variables to individual numbers, and the other extreme where we only had the sign lattice that was really very coarse-grained and approximative. So an interval lattice is basically representing numeric values by intervals. And let's assume at the beginning that we have only very simple intervals. So this is the interval only containing the natural number 0. And this is the interval only containing the natural number 1, for instance. Now, what's interesting is that we can, what's interesting is we can arrange these different domain values in a lattice like you can see here. So for instance, we can very easily merge the interval with only 0 and the interval with only 1 to the interval containing all the values between 0 and 1, including the values themselves, right? We can do that for all the other values that you see here. And then we can continue doing this, right? So we can also merge these two intervals to this one, and they get larger and larger, like you see here. And we can continue doing this and actually forever, right? So this is an infinitely high lattice. And eventually we can have some conceptual top element, at least, which is the natural numbers, including 0, right? And we could also have some top element that says, well, basically, I don't know anything about the particular interval yet. Okay. I'll get back to this because this will give us some challenges. But I also want to talk about some other frequently used lattices first. We have already briefly talked about the powerset lattice, right? So in particular, whenever you have a set of some elements, you can define a powerset lattice like you see it here. So it's basically containing the all the different subsets of the original set. And there's a natural partial order, which is basically subset relationship here, right? So the set 0 and 3 are in an order with this set here because they are subsets of 0 and 3. And this naturally happens to form a lattice. So you can always use a powerset lattice over a set of values. You always have the guarantee that it isn't a lattice if you use the subset relationship as your partial order, and that's very useful. Now, if you have such a lattice, we can also compute its height. And here in the powerset lattice, we're actually guaranteed that the height is finite for a finite set. And in particular, it's bounded by the number of elements in the original set. So you cannot get any higher than this. And this is important. So in general, the height of the lattice is important because it also means something about how quickly your static analysis might actually terminate or not. You can imagine in each iteration of your static analysis, you might be conducting these merge operations. So from such to sets, for instance, you might be moving to this set here. And in each new iteration, you can do this one more time and one more time. But you can only do it so often because at some point you're going to hit this top element. And the higher your lattice is, the longer that might actually take. We've also already talked about mappings, and you can actually very naturally form a so-called map lattice. So if A is a set and L already is a lattice, then you can obtain such a map lattice that points from elements or that maps from elements in A to lattice elements, right? So basically you have such a mapping here. And this is ordered just pointwise. So, you know, two elements here are in order if their lattice elements are in order. And it also means that your upper and lower bounds, they can be computed pointwise as well. And the height of this particular lattice is then the number of elements in A times the height of this lattice L. So also that is pretty much bounded. As an example, you can think of such a map lattice here where A is the set of program variables and L is the sign lattice, for instance, right? We already saw this earlier. Also very common is a so-called product lattice. So also here we assume that we already have lattices L1 to Ln, let's say. And then you can have a product lattice out of this. So you're simply constructing a Cartesian product. So it means you're forming a new lattice whose elements are tuples, n tuples in this case. And each individual element is an element of these lattices that we have defined already. Also here, the partial order is defined pointwise. You can compute the upper bound and lower bound pointwise. And here the height of this combined lattice is actually the sum of the heights of all the individual lattices that we have there. And this is also very useful because, for instance, if you are computing lattice values throughout a procedure in a program analysis, then we basically have a mapping, for instance, for every single statement. And then you could take the number of statements as your n, and you can basically have a combined lattice that combines individual lattice elements for every single statement. But you get the guarantee that the computation over all statements also again forms a lattice. And it can be computed basically in these time bounds here. You can also have flat lattices. That's sometimes useful as well. So a flat lattice of a set A, it looks like this, right? So it simply has all the different A elements. And they are arranged in such a flat manner, and you still have a bottom and top element. And the height of the flat lattice is just 2 because you can have these 2 merge operations basically until you hit top. Now for static analysis, to terminate these lattices, they must be bounded. And that brings me back to some of the original examples that I showed you. Let's revisit this example that I showed you earlier here. Okay, so I already showed you what happens when you iterate through this program here with the assumption that we are just propagating these sets of numeric values here. But now let's assume that we actually have a mapping from a variable not to a number anymore, but this is now actually an interval. Okay, so here 0 is the interval that only contains the number 0. And we are propagating this here. And now here we get the interval only containing 1. And now we're actually conducting a merge operation again. Okay. And now the nice thing is that the lattice, it immediately tells us how we should merge. And by looking at this interval lattice again, we know that we should merge the interval 0 and the interval 1 to the interval 0, 1. Okay, so this is going to be our new right-hand side value that we are computing here. Okay. Now we have this interval, and we now know that we have a number between 0 and 1, and we are incrementing it. So that means, as a result, we now know that we are now looking at a value between 1 and 2. Okay. So we've basically just moved from one lattice element to another. And now we are merging again at this point here. Okay. And now we have to merge these two intervals. And we are merging it to this element 0, 2. So that's our new domain element or our new lattice value that we have here. Now, you can already see that we can continue doing this, right? So this is still not quite what we wanted, because now we can get domain element 1, 3 here. And again, we could continue merging this, and essentially these two lattice values, they can always be merged, and that's nice, but we can continue doing this, right? And this has to do with the fact that this particular lattice that I showed you, the one with the intervals, that actually has an infinite height, right? So all the other ones I showed you, the powerset lattice, the map lattice, and so on, they are finite height lattices, assuming that the sets on which they are constructed, they are finite. But the interval lattice, by its very nature, it's not. So you can still have infinite recursion. And that's really the problem here, right? So normally the lattice must be bounded for the analysis to terminate. But here we have so-called infinite ascending chains. So you can always continue merging. And that is a problem. So we must demand that any ascending chain in your lattice must be of finite length. And it actually suffices that every ascending chain eventually stabilizes. That is the so-called ascending chain condition. If we know that this holds, then termination is actually guaranteed. So just to recap, so I showed you that by arranging lattice values, or by arranging domain values in a lattice, we get this guarantee that you can always merge two lattice elements. So you always can merge them to unique upper bound. And by demanding that we have this ascending chain conditions, we can basically make sure that we can only do this a finite number of times. And because we can only do it finitely often, then we know that the analysis must eventually terminate, because then eventually we will be merging two elements that we have seen before, and then we are guaranteed, therefore, to also reach a fixed point. As a next step, I want to talk a bit more about flow functions and some additional property that we also need to ensure on these. But I'll do this in the next video. See you then.